Welcome everyone. In this video I'm going to continue my tutorial series, and this time I'm going to discuss timers and PWM. Previously I have already discussed the basic USART functionality, and then before that I also discussed the basic GPIO functionality of this chip. And now I think it's time to focus more on timers, because they are quite important and very useful peripherals of this microcontroller. This specific microcontroller that I'm using has two timers, one general purpose timer and another advanced timer, and I will use one of those to introduce you to some basics regarding timers and PWM. So in a very basic approach, a counter can count up or down, and it counts up once for every clock pulse. And this clock pulse is generated by the system frequency, which is the frequency of the chip, and in our case this is 48 megahertz. And the timer's resolution is also important, because that tells us how high it can count. So we typically have 16 or 32 bits timers, and they can count up 2 to the 16th or 2 to the 32nd power before overflowing or rolling over back to zero. And then to keep track of the counter, we can use the CNT register value. So for example, when we start the counter, we can check the value of the CNT, and based on the counter's frequency or period, we can determine how much time elapsed, for example. So one period for the timer, if we don't use any prescaler, and that would be the fourth parameter, which I'm not mentioning right here, but I will show it in the examples. So the clock frequency gives us a period, and that period on this illustration is basically the time on this scale right here. So this is, let's say, I write it out, one period. And how that is derived is very simple. That is just 1 over 48 megahertz. And that is roughly 20.83 nanoseconds. So every, let's say, 21 nanoseconds, the counter is incremented by 1 if there is nothing else set. For example, as a prescaler or other values which can influence the speed, how quickly the counter is incremented or decremented. And actually based on this, we can calculate any kind of time periods that we want to count up for, and we can determine the other parameters of the timer. But let's talk about the other two registers first, which are closely related to the timer. First I will talk about the ARR, which is the auto reload register. And this value is nothing else, it's just the final value of the counting. So after the counter, so the CNT value reached this value, the counting restarts from 0. So it automatically reloads. And that's what we have here. And that is actually, if we look at the PWM output down here, determines the period of the PWM signal. So basically this length, and this is one period, as it is also shown here. So that's a full period. So from count 0 to count where ARR is count, or actually the other way around, but when these become true, then that is the period. And then we have the CCR, or capture compare register, and that is basically when your PWM signal changes sign. Because based on how you set up the PWM output, you can start with a high level, like I did it in this example, right here, or you can start with a low level. And then when the counter, so this guy here, reaches the value of the CCR, so basically this is true, then the PWM output flips signal. In this case goes high to low. And then it continues until it reaches the condition right here, and then it starts over. And then you created the basically the PWM signal, the periodic PWM signal. And we can derive two parameters based on the register's values. And one is the output frequency, obviously. So this is the PWM output frequency, and that is nothing else than just the system frequency. So that is the 48 megahertz divided by the prescaler plus 1 times the auto reload register plus 1. And these plus ones are there because of how the registers are manipulated. But the product of these two expressions in the parentheses will be the divider for the F system, and that will ultimately determine the output frequency. And I will show you this through several examples, how it's done. And once we determine these parameters, then we can also assign a duty cycle to our PWM. And that is nothing else than just the CCR value. So this guy, which I showed you, that determines when the PWM basically changes sign, divided by the auto reload register plus 1. And actually, this is just a non-integer number. And if you want to make it, let's say, an integer or kind of integer, or make it as a percentage value, because this will be actually expressed as a percentage, then you just multiply it by 100. So if this expression becomes 0.5, then of course the whole expression will be 50 and then percent. And you can see that the CCR divided by ARR plus 1. So if I say that the CCR, let's say I do it in the middle just to make it more visible. So this was 50, and this was, the ARR was set to 99, but we have the plus 1 there, so that was 100. Then obviously you divide 50 by 100, which is 0.5, and then you get the 50% duty cycle, which is like roughly illustrated on this drawing. So you can calculate back and forth, and you can determine the duty cycle. And then, for example, that will be useful in the future if you want to generate an output signal for driving a motor and regulating its speed, or you want to regulate the brightness of a LED or something like that. So I think I showed you how this works roughly, and what are these different registers as the CNT, CCR, and ARR, and what their values do. So let's go to the Maun River Studio and let's develop a code which actually implements these actions and shows us how it's done. Alright, so here's the studio, and let's do our usual exercise. So I open a new project by selecting my microcontroller family and selecting the actual microcontroller F4P6. And then this is part 3 of the tutorial series. And we will talk about timers and PWM. So our file is here, and as usual, this already has the useart functionality implemented, and we will use this, so I keep it in the code. However, I remove a few parts which I don't need. For example, I don't need this variable here. And I want to get rid of these things, and these things, and then this thing. And as usual, let's print something on the serial terminal. I can even add the delay just to have enough time to switch between this user interface and the serial terminal. So let's say after 5 seconds this message will pop up. And this is done. So the first action that we have to take here is that we need to create a new function which will take care of the timer. So let's call it like this. And then actually I want to be able to pass parameters to this function. So let's implement that part as well. And I want to be able to pass 3 parameters. Prescaler value, auto reload register value and capture compare register value. So those are unsigned integers. And then PRSC. Then I just copy paste this and it will be ARR and it will be CCR. So this is nice. So I can then call this function with the 3 parameters in it, and that will allow me to already start the function with a certain set of values, so it's easier. So first of all, we need to enable the peripheral clocks for GPIOD and TIM1 or timer 1 to be able to use them. So RCC underscore, and then we use the advanced peripheral bus 2, so that is this guy right here. And then we need the peripheral, which will be GPIOD, because I will use this for toggling a pin on this port. And then I just combine this also with TIM1, which is the timer 1. And the new state should be enable, because obviously we want to enable it. And line is closed. Then let's take care of the timer pin first. So first we create a structure for it, or initialize the structure for it. And then we need to configure 3 different modes: the pin, the mode, and the speed. So what we can do here is that we know that we want to manipulate this guy here. So this dot GPIO pin, and I will use this on GPIO pin 2. So that's that. And then we have a GPIO mode. And since this will be using the PWM function of the timer and not the, let's say, native function of the pin, we have to declare this as an alternative function for the given GPIO mode. So that will look like something like this, and this will be this. So what this means is that the GPIO pin's mode is the alternate function and push-pull. The alternate function means that we don't use the primary function of the pin, that's very obvious, and PP means push-pull, which means that we can set it to a determined state, high or low. And then we just have the speed left, and let's say the speed can be 30 megahertz. It doesn't matter in this case. And then we initialize this. So it will look like this. So we need to initialize the GPIOD, and then we pass the structure to this function, or its memory address basically. So something like this. And then we can focus on the timer. So first of all, I want to disable the timer because this function will be universal and we will be able to call it several times. And whenever we want to manipulate its, let's say, parameters, we first need to stop the timer. Actually, we don't need to. We can do it other way around to update the timer like on the fly. But I just want to do it like this because it's a bit simpler to take care of. So we know that we have the timer 1, and this should be disabled. Because it can be that we call this function when the timer is already running. So then we want to start with a clean, let's say, status of the timer. And then we need to take care of the time-based part of the timer and the output capture part of the timer. So they both need their structures to be initialized and then configured. So we have this guy, which is right here. And then we just give some name to it. So this will be and now I did a syntax error here. So now this looks fine. And then the same for the time base. This already exists on the dictionary. Equals 0 right there. And now we have to fill these in. Let's start with this. So let's say we want to fill in the period. The period, if you remember from the sketch that I drew, that will be the ARR. And then actually we have a prescaler. So that's the PRSC. And then we need to take care of the clock division, which will be tim CKD, and I think it's this one, which means that there is no division of the clock. And then counter mode, which means whether we should count up or down, and we count up. So the counting starts from 0 in this case, and we go up. And then we pass this to the corresponding function. And now we have to take care of this guy here, the output capture part, which takes care of the PWM signal actually. So here we have the output capture mode, which is OC mode, and it should be PWM1. So this is the PWM signal generation enabling line basically. And then we need the output state as well, which will be enabled. And what this does is the following. So we can generate actually the signals internally, which means that the PWM signal will be enabled and it will be generated, and you can wire it to another peripheral. For example, you can trigger an ADC with it, so it will convert, let's say, every rising edge of the PWM signal, and then you don't need to have it on an output pin. But I want to have it on an output pin, and this line actually enables it to be, let's say, driven to an output pin. And I will need this because I want to measure the frequency and also, let's say, toggle an LED with it. So that's why I need this. And then this, if you remember, the pulse is the length of the signal half. So either one half or the other half will be related to this. And actually this is the first half, because this will be the CCR. And half doesn't mean 50% right here, because actually the value of this CCR will determine that percentage. That is the duty cycle. And then this will be also interesting, because this is what I talked about, that the PWM signal can start either high or low. So I make it to start high. So when you start the PWM, the beginning of it will start high. So actually, for the length of this value, it will stay high. And then for the rest of the time, until the counter reaches the ARR value, it will stay low. So this is done. Let's initialize this. So this is very cool, but we still haven't enabled the output. So let's do that. Like this. So the PWM will be on timer 1. And obviously it has to be enabled. Then enabling this parameter means that when we change something on the OC register, it will not take an immediate effect, but it will be only applied on the next update event, which can be, for example, a timer overflow. And the same applies for the ARR register. When enabled, the ARR value won't take an immediate effect, but it will be preloaded and it will be updated on the next update event when the timer overflows. We actually enable the timer itself, because this line just enabled the generation of the PWM, but it did not start the timer. Here we start the timer. So now let me do this, and let me put it here in the setup part, so it will just run once. Let's talk about the prescaler. So that is used to bring down the original clock frequency to another frequency, And in this case, the 48 megahertz will be divided by this value to have a lower value. And let's say I want to have 1 kilohertz here. And to do that, I need to divide the 48 megahertz with 48,000. So I just do this for fun, but this is actually not valid. You should either print this because there is a hidden +1, or simply do this. I usually like this practice that I already calculated in my head to know that there is a +1. So I have to just do this -1 here. So now we know that our frequency will be 1 kilohertz, and then we can determine, okay, how long we want to count up. And 1 kilohertz is exactly 1 millisecond period. So let's say I want to count up to 200 milliseconds. So that will be 199 because the +1. And then I want to have 50% duty cycle. So there actually I have to put in 100. So if I did everything correctly, this will initialize the timer. So let's see if this compiles first of all. And let's upload this to my board. And now I change cameras so you can see what is happening with the board. So what you can see here, I have an oscilloscope and it is showing 5 Hertz and 50 duty cycle or 50% duty cycle. So first of all, we created a lower frequency by dividing the system clock frequency 48 megahertz by 48,000. So that is 1 kilohertz. And then we know that from 1 kilohertz, that is 1 milliseconds of period. And then we want to count up to 200 of these periods, so 200 milliseconds. So with that, if we take this 200 millisecond and take its reciprocal value, that will be actually 5 Hertz. And then we also said that after 100 counts, we should flip the value of the PWM signal, and that is actually the 100, the third parameter in the function, the CCR value, and it seems to work fine. So you can see that we have a 5 Hertz signal and its duty cycle is 50 Hertz. So that's really nice. So now the next logical step for me would be to make this line more dynamic in a sense that we could update those 3 parameters from the serial port. And we learned this almost exactly in the previous lecture. So let's apply that knowledge and let's make this function a bit more fancy by being able to update it on the fly. So first I want to create a function which polls the USAR port and captures whatever I send to it. No parameters. And then we just simply look for the RX flag and its change. And that we know from the previous lecture how it looks like. And we are reading USART1 and we are looking for the RX flag. And then when that flag is set, so when it is not reset anymore, then we do our stuff. So we create a character and let's call it received character. And that is the character that we read just right now when the flag changed from the USART1. And of course that has to be equal to it. So whatever character is returned by this function is passed to this received character variable. And then we have to check this. What is it? Because based on the outcome, we have to do different things. So if this received character is an end line character, that means that our message is finished. So we actually pressed enter on the computer terminal. Then we have to let the microcontroller know that now it's enough reading. Let's parse these numbers. So what we do here is actually we have to fill in a buffer. So let's create a buffer. Maybe I do it with small characters so I don't confuse stuff here. So what we do here is that if the last character that we received was the end line character, then we put the null terminate character in the given index where we are at. And then let's say we create a function which will parse the USART. And then we reset the buffer index, because the next message will have to start from the beginning of the USART buffer. And we need an else block here, because if it was not an end line character, we have to keep filling up the buffer. So then, let's say 100 minus 1. We will never send this many characters, but let's do it like this. And then we do it like this. So what we do here is basically that if the buffer index is less than 99, and why I put this 100 minus 1 there is because of the last character, the null terminate character. So if we still have, let's say, space to fill in our buffer, then we just add the most recently received character to the next place in the buffer. And then you can see that the compiler is complaining because these two guys don't exist. So I just copy this. I go to the global variables here. And let's do it just like this. So buffer index is 0 and the USART buffer is 100. And this is a buffer of characters, and this is just an integer. We don't care about what kind of integer this is. So now there is no complaint here, but I'm complaining because this guy is not really existing right now. So let's implement it, because we need to parse the stuff. So we need to take care of 3 variables that we are going to parse, and that is the prescaler, actually just to indicate that it's a local variable. And then we have ARR, that is also 0, and then CCR, which is also 0, right? And then we use the scanf because it's very easy to use. So we scan from the USART buffer, and what we have here is 1 decimal, space, another decimal, space, and another decimal. So we will send the message in this format, and then we will pass these values to the prescaler, and then to the ARR, and to the CCR. There, done. So the message will be, for example, this. And then we print them just to check that we parsed the proper values. So the parsed values are, and then, so we have 1 decimal, and another decimal, and another decimal, and we put a line break there so we can print it in a new line. So we have this guy here, we have this guy here, and we have this guy here. Cool. And then we have to initialize the timer based on this guy, and this one here. And just a reminder, I removed the initialization here, and instead I initialize the timer here freshly with the newly parsed values. So what I need to do is we have to pull the USART, and we have to pull it here like this. So no errors, and I could upload this. So let me open the terminal, and let me show you the camera. So I think I started everything. We can see the message on the terminal. So let's actually send the same numbers that we have here. So the 47,999. And then we have 199 and 100. And let's just start this. and after some adjustments we can see the signal nicely. So you can see that the terminal returns the correct values that we expect, plus we can see that we have 5 Hz and 50% duty cycle, which was the exact same value that we set when we set the timer manually. And now let's set another number, let's say 99. And before I type the next number, first let's consider what would happen with the 99. So 99 will become 100. So if you remember, when we divided the 48 megahertz with 48,000, then we got 1 kilohertz frequency for our timer. And that means that we have a period of 1 millisecond. And the second parameter is the ARR parameter, which tells you how long the counter will count up before it resets to 0 and starts the counting again. So when we counted up to 200, then we got 5 Hertz. That is because 1 over 200 milliseconds. And now we count to 1 over 100 milliseconds. So the frequency should double. So we could expect a 10 Hertz signal. However, now I cannot enter 100 here because that would cause a funny duty cycle, right? So in order to maintain the 50% duty cycle, we need 50 here because that's half of the ARR register. So let's send this value to the microcontroller. So now, as you can see, we have a more rapid signal. So it's 10 Hertz and the duty cycle is 50, as we would expect. So that's really nice. And we can also play with the divider. So we can further increase the frequency by sending another divider. So far we divided or pre-scaled by 48,000. So let's do it with 24,000. And let's maintain a 99 and 50. And just simply let's see what happens. So now you can see that we doubled the frequency because we halved the divider. So now we have 20 Hertz. So by following this principle, I can send 12,000 and I can send 99 and 50. And that should be, if I'm not wrong, 40 Hertz, but let's see. And that is 40 Hertz. So now we have a stable 40 Hertz signal with 50% duty cycle. And then I just go back to the original frequency because it's easier to demonstrate on that because I'm lazy to change the parameters on the oscilloscope. That we have now a wide fat signal there. And you can see the duty cycle based on these two waves or half waves. So what I'm trying to do here is, for example, if I send this number and I say 25, and you can see that I chopped off the duty cycle. And I say 150, then I made a much larger duty cycle. Now it's 75%. And 50, so that's 1/4 of 200, so that should give us 25% duty cycle. And there we are, 25%. So now you can see how the duty cycle works as well. So you can see that it's very easy to generate PWM signal, and it's very easy to make a function which sends the parameters via the serial terminal and then adjusts it on the microcontroller itself. So now let's do something else, and let's implement a blinking LED without delay. This is already that, but actually this is not how I want to implement it because this is now pure PWM signal generation, but there is a better way to do this, and I want to show you how to do that. So let me get rid of this, and let's create another function for the timer. So this will be a timer that we will use for delay, and let's just do some recycling. So I just copy this wall stuff, throw it in this here, and then I tell you what we need. So we still need this because we need to enable the clock for the peripherals. And then I kind of need this, but now I use the LED as output PP. And why I use this is because previously we used the GPIO pin as PWM pin. We don't use that as PWM pin anymore, we just want to toggle it, but not with the PWM, so that's why I remove this functionality. And together with that, I also don't need the PWM related functions or structures and so on. So I remove this guy here, and I remove all of these right here. So this is fine so far. And then I will just do this manually because of reasons. So the period will be 20,000. And here that the period is not really relevant because I will never actually want to get the counter go beyond this value. But I just want to have a reasonably high value for the period. What is more important here is to declare a proper prescaler value. So what I'm going to do here is I'm going to divide 48 million, so 48 megahertz, by 9,600, so 9599. And why I do that is the following, because if I divide 48 megahertz by 9600, then I get actually 5 kilohertz. Now I don't care about the capital letters, or yeah, I do. So it will be like this. And if you take the reciprocal value of 5 kilohertz, that will be 200 microseconds. So what this does here is that the timer will create a tick at every 200 microseconds period, or every 200 microseconds passed. And then after 200 microseconds is passed, the timer's counter is increased by 1. So every 200 milliseconds we increase the timer's value by 1. So you can calculate backwards, and then based on this, let's say, multiplier or parameter or factor, you can decide that, okay, I want to count up to 1 second exactly, and then I want to do something. And how you do that is that you divide 1 second by 200 microseconds, and that will give you 5000, which means that the clock has to count up until 5000 in order to do something. And we will do it like that. So let me further clean up this function, because we don't have PWM, we don't have this, and we don't have this. Now we don't need it simply. And we create another function which will poll our timer, and it will require a parameter which will be called, let's say, elapsed ticks. And then if the timer one's counter is greater or equal than the elapsed ticks, then we do something. So here, as the following example, if we want to have like 1 second with our current setting of the timer, this guy here, that will require 5000 ticks. So if we enter 5000 here, then when the counter counted up to at least 5000, then the function or the block, if block, enters this part which I selected. And then we just toggle the LED that we already used in the PWM example. And how we do that is the same way as we did it in the previous lectures. So we write bit on the GPIO D, we have pin 2, and then this becomes the same exact cheating way that I did in the previous lectures. We first read the output data bit register value on the same port and on the same pin, and return its opposite. So we check if it's bit set, then we return reset. Otherwise, if it was reset, then we return bit set. So this toggles the switch. This line looks into the register, checks what is the value, let's say it's 0, then it sets the next value to 1. And then if the next value is 1, it sets it to 0. So it bounces back and forth with each iteration. So if the timer reached our value, we have to reset the timer. So we set the counter on the timer one basically back to 0. And for fun, we print this. That we say that that the timer tick occurred, or something like this. And let me compile this. So it compiles, but we need to pull the timer. So let me place it here. And we agreed on 5000. So this is 5000 times 200 microseconds equals 1 second. So in the beginning, the pin is high. After 1 second, it will be low. And after another second, it will be high again. And this high, low, high is one full wave. So actually this will also occur on the frequency, because the frequency will be different than you would expect. So compile again, and then this is fine. However, we need to initialize this timer, obviously. So let me put it here, compile, and upload. And you might want to see the camera as well. You can already see that the terminal is doing something. So let me adjust the oscilloscope. And now I managed to fix this more or less. And I just cleared this. So you can see that every 1 second the timer is ticking. So we actually get the message from this line in line 166 that you see in the background. And you can see that we have basically a half hertz signal. And that is exactly because of this toggling that I explained, that in the beginning the signal is high for 1 second, and then it's low for another second. And then after 2 seconds it returns to high, completing a full cycle. So the period is actually 2 seconds, and 1/2 is half. So then in order to double the frequency, we need to count only to 2500. And then let's see if this works. It might take some time for the microcontroller to catch up, and also for the oscilloscope. And there you can see that now we have a more dense set of waves. And then this supposed to be 1 hertz. So I stop the trigger, and then you can see that this is 1 hertz. And of course, the further we decrease this, the higher the frequency becomes. So let's say I set it to 500, so that's 1/5 of 2500. So it should be 5 hertz frequency. We will see if this works at all. After like 5 seconds it should start. Yeah, so it started, but the oscilloscope might need some time to catch up. And if I adjust the time scale, then it looks much better. And then here you can see how quickly it updates the terminal. So that's like 5 updates per second. And then this way, actually, you can define the tasks, so they don't have to wait until the delay time passed, but instead they just poll the timer, and when the timer counted up to enough time, then the tasks can run. So for example, now I'm blinking an LED quite often, but I don't have any delay in between 2 blinks. And that is very good, because it's not blocking the rest of the CPU. So you can do other stuff between 2 blinks, or between 2 sensor readings, and so on, without actually blocking the code. Because when you apply the delay, then the code is not doing anything else. It's just waiting in that specific line. But here, the while is running over and over, and then it just pauses the timer, and it only does the task, in this case printing on the serial port, as you can see, when it is needed, and in the meantime it does everything else. And then basically this is it. This is what I wanted to show you here. So first we learned how to generate a PWM signal using a timer, and then we also learned how to send the parameters for the PWM signal generation via USART. And then I showed you how to create a delay using timers and without blocking the rest of the code. And that is also very useful, because then you can do certain tasks when they need to be done, but you don't need to wait for them, let's say using a delay, but you can just configure the timer, and based on the elapsed time you can generate an action. For example, blinking an LED or running a function that reads out a sensor or something like that. So for example, you have a temperature sensor attached to the microcontroller and you want to read it every 1 second. You don't need to delay for 1 second and then read it and then update the display, but you can do something else. For example, read another sensor and then read the other sensor, like the temperature sensor, after 1 second elapsed, and then jump to the next task. So using timers is very good, and this is just a fraction of the functions that they can do. But if I would explain everything in one simple, let's say, introductory lecture, it would make it very long and very difficult. So I just show you the basic functions, and in further lectures, when we learn more and more, and we need to return to the more advanced functions of the timers, I will explain those as well. As usual, I published a lot of resources on my website, so please check the link in the description and visit my website, because you will find a lot of extra information there. And also don't forget to visit the previous lectures, because they might contain information which are mentioned here but not explained here, because I assume that you have already went through the previous lectures. And if you like these kind of contents, please don't forget to subscribe to my channel. That helps me a lot. And if you want to help me further, then you can sign up as a member to my YouTube channel, and you can use my affiliate links on my website in order to buy, for example, this microcontroller or other gadgets. I hope that this video was useful to you. I hope you learned something, and see you in the next video.